Hi, I am Dinesh, working as Assistant Professor, Department of Physics, Government First Grade College, Sagara. Dear students, in this video lecture, I am going to explain the topic Electrical Instruments and Measurements. Here in this chapter, I am going to explain in detail about the instrument Ballistic Galvanometer. Dear students, see, this is actual instrument which is used in our laboratory. This is Ballistic Galvanometer. See, galvanometer is a device used to measure and detection of an electric current. Galvanometers can be classified as deadbeat and ballistic. Galvanometers are electrical instruments. Let us see the ballistic galvanometer. Ballistic galvanometer is an instrument used to measure the total charge that passes through it in a given time, not as a steady current but as a sudden discharge. There are two types, namely, first one, the moving magnet ballistic galvanometer, second one, the moving coil ballistic galvanometer. Let us see the moving coil ballistic galvanometer in detail. Here, an ordinary galvanometer is intended to measure the strength of a steady current. A ballistic galvanometer is intended to measure the quantity of charge that passes quickly through the coil, not as a steady current but as a sudden discharge. For example, in the discharge of capacitor and in electromagnetic induction. See, this one is electromagnetic induction coil. When the discharge takes place, it flows through the coil for a short time, and hence the periodic time of the swing of the coil should be greater than the time for which the charge flows in the coil. For this purpose, the galvanometer should be so designed as to the following features, like first one, the time period of the galvanometer must be large, and second one, the damping should be small. We know that the periodic time is given by the formula T equals 2 pi into square root of I upon C, where I is the moment of inertia of the coil, which should be large, where C is the restoring couple per unit angular twist, must be small. To reduce the damping, the coil is wound on a non-conducting frame, such as ivory or ebonite or bamboo. Dear students, let us see the construction, working, principle of ballistic galvanometer. Here, the principle of ballistic galvanometer. When a conductor carrying a current is suspended in a magnetic field, it experiences a force. And the direction of the force is given by the Fleming's left-hand rule. This is the main principle of ballistic galvanometer. Here, according to the definition, the galvanometer, which is used for estimating the quantity of charge flow through it, is called the ballistic galvanometer. We know the working principle of the ballistic galvanometer is very simple. It depends on the deflection of the coil, which is directly proportional to the charge passed through it. The galvanometer measures the majority of the charge passes through it in spite of the current. Let us see the construction of ballistic galvanometer. Here it consists of a rectangular coil. See in the diagram, it consists of rectangular coil having a large number of turns, of thin insulated copper wire wound on a non-conducting frame. This coil is suspended between two pole pieces, that means strong horseshoe magnet, with the help of Pasper bronze strip. This one is Pasper bronze strip. The other end of the coil is attached to a spring. Made of Pasper bronze wire. A soft iron cylinder is placed within the coil. This one is iron core, to make the magnetic field between the two pole pieces strong. A mirror is fitted to the coil, which is used to read the small deflections with the help of a lamp and scale arrangements. The whole arrangement is placed inside a metallic box provided with a glass window and leveling screws. Due to momentary charge, coil gets an angular impulse which sets the coil in motion. This is about the construction of galvanometer, ballistic galvanometer. Let us see how it works. When the charge passes through the galvanometer, their coil starts moving and gets an impulse. The impulse of the coil is proportional to the charge passes through it. The actual reading of the galvanometer achieves by using the coil having a high moment of inertia. The moment of inertia means the body opposes the angular moment. If the coil has a high moment of inertia, then their oscillations are large. Thus, accurate reading is obtained. Let us see the theory of ballistic galvanometer. Dear students, consider a rectangular coil. See rectangular coil in the diagram having n number of turns placed in a uniform magnetic field. Let I be the let L be the length and B be the breadth of the coil. Here length and breadth. Length is L, breadth is B of the coil. The area of the coil is given by, that is A is equal to length into breadth, that is L into B. Let it be equation 1. When the current passes through the coil, the torque acts on it. The given expression determines the magnitude of the torque. Here the torque is given by the formula tau equals Ni into B into A, NIBA. Let it be equation 2. Let the current flow through the coil for very short duration, says dt, and it is expressed as tau dt equals NIBA dt. Let it be equation 3. If the current passing through the coil for t seconds, the expression becomes integral of tau into dt between the limits 0 to t is equal to NBA integral of I dt between the limits 0 to t. This is equal to NB A into Q. Here integral of I dt between the limits 0 to t becomes Q. the charge Q with the through the coil, the moment of inertia of the coil is given by I, and the angular velocity through omega. The expression gives the angular momentum of the coil. The angular momentum is equal to I omega. Let it be equation 5. The angular momentum of the coil is equal to the force acting on the coil. Thus, from equation 4 and 5, we get I omega equals NBAQ. Let it be equation 6. The kinetic energy, it is indicated as K, deflects the coil through an angle theta, and this deflection is restored through the spring. Therefore, the restoring torque is given by 1 by 2 C theta square. That means half C theta square, and kinetic energy of the coil is of I omega square. See, due to angular velocity of the coil possesses a kinetic energy of I omega square and is brought to rest by performing work in twisting the suspension wire. If C is the restoring force per couple per unit twist, then the equations are written as like this: restoring torque and kinetic energy K. Dear students, the restoring torque of the coil is equal to their deflection. Thus, the restoring couple of C theta square is equal to the of I omega square restoring energy. Therefore, 1 by 2 get cancelled. Then this equation becomes C theta square equals I omega square. Let it be equation 7. The periodic oscillation of the coil is given as T equals 2 pi into square root of I by C, where I is the moment of inertia of the coil, which should be large, and C is the restoring couple per unit angular twist, must be small. Therefore, on squaring, this becomes, above equation becomes T square equals 4 pi square into I upon C. Therefore, on simplification of this equation, we got T square by 4 pi square equals I by C. That is C T square by 4 pi square equals I. That is moment of inertia I. By multiplying the equation 7, above equation 7, from the above equation we get C square T square theta square upon 4 pi square equals I square omega square. Finally, we got C T theta upon 2 pi equals I omega. Let it be equation 8. On substituting the value of equation 6 in the equation 8, we get C T theta upon 2 pi equals NBAQ. That is Q equals charge. Q equals C theta T upon NBA 2 pi. Let it be equation 9, where Q is equal to CT upon 2 pi BNA into theta. Let K equals CT by 2 pi BNA. Therefore, Q equals K into theta, where K is the constant of the ballistic galvanometer called the reduction factor. The reduction factor is the current required to produce unit deflection. Let us see the calibration of galvanometer. See, this diagram represents the calibration of ballistic galvanometer with capacitor C. Here the capacitor is connected like this with resistance, high resistance R, and ballistic galvanometer and high resistance are in series, and there is a dual switch, and it is connected to the EMF, battery of EMF E. Here the calibration of the galvanometer is the process of determining its constant value by the help of the practical experiments. The following are the methods used for determining the constant of the ballistic galvanometer. Here there are two methods. One is using a capacitor. Second one is electromagnetic induction coil. Let us see the using of capacitor. The charging and discharging of the capacitor gives the values of the ballistic galvanometer constant. The circuit arrangement for the calibration of ballistic galvanometer using the capacitor is shown here. Here the circuit uses two-pole switches S, two-pole switch S, and the unknown EMF source E. When the switch S connects to terminal 2, when it is connected to the terminal 2, then the capacitor becomes charged. It becomes charged. Similarly, when the switch connects to the terminal 1, then the capacitor becomes discharges. When the switch terminal connected to the terminal 1, then the capacitor starts discharges through the resistance R. Through the resistance R connected in series with the ballistic galvanometer as shown here. Then the discharge current of the capacitor deflects the coil of the ballistic galvanometer through an angle theta. The formula calculates constant of the galvanometer, that is K equals Q upon theta 1, that is equal to Q means C into E. According to the principle of capacitance, that is Q is equal to CE upon theta 1. This is coulomb per radian. K is measured in the unit coulomb per radian. This is about the using a capacitor, calibration of galvanometer. Let us see the damping correction. Damping correction of the galvanometer. Here damping means the amplitude of successive oscillations therefore goes on decreasing. This effect is known as damping. The amplitude of successive oscillations goes on decreasing. That effect is said to be damping. Generally, the motion of coil is opposed by the resistance of air, and second one, induced EMF in the coil. Let us see. Dear students, we know that the formula, the charge Q, the ballistic galvanometer is Ct upon 2 pi BNA into theta. Already know this one, equation 9. While deriving the equation 9, we have assumed that the whole kinetic energy imparted to the coil is completely used to twist the suspension wire. This is not exactly true. In actual practice, the motion of the coil is damped by air resistance and induced current in the coil. The first throw of the galvanometer is therefore smaller than it would have been in the absence of the damping. So, it is necessary to apply a correction for damping to the first throw of the galvanometer. See here, the throws are measured like this, that is theta 1, theta 2, theta 3, theta 4, theta 5, theta 6 and so on, like this. From mean position to left side and right side. Left side, mean position, right side. Here these are the throws, left side and right sides. Let theta 1, theta 2, theta 3, theta 4 and so on be the successive maximum deflections from the zero position to the right and left as shown in the figure. Here theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. During throws, it gives the maximum deflections from 0 position, that is mean position, 0 position, to the right side and left side. Then it is found that theta 1 by theta 2, theta 1 by theta 2 equals theta 2 by theta 3 equals theta 3 by theta 4 equals theta 4 by theta 5 and so on equals D. Let it be D. Let it be equation 10. Where this D is a constant called the decrement per half vibration. Decrement per half vibration. Let D equals e to the power lambda. Then lambda equals log D, log to the base e into D, where lambda is called as logarithmic decrement. Logarithmic decrement. Here decrement of the swing is defined as the ratio of two successive deflections, one to the right and the other to the left. Thus, for a complete oscillation, theta 1 by theta 3 equals theta 1 by theta 2 into theta 2 by theta 3 equals d square is equal to e to the power of 2 lambda. See here, let it be equation 11. For 1/4 of an oscillation, the RHS of the equation 11, RHS, right hand side of the equation 11 is e to the power of lambda by 2. E to the power of lambda by 2. Let theta be the true first throw in the absence of damping. Theta be the true first throw in the absence of damping. The actual first throw in presence of damping is theta 1, which is observed after the coil completes a quarter of vibration. Thus, the decrement for theta is given by the formula theta by theta 1 equals e to the power of lambda by 2. Let it be equation 11a. Taking fourth root of the equation 11, we get theta 1 by theta 3 whole to the power 1 by 4 equals e to the power lambda by 2 equals theta by theta 1. This is equation 11a is used here. This equation 11a. Theta by theta 1. This one is theta by theta 1. That is theta 1 by theta 3 whole to the power of 1 by 4. Therefore, theta equals theta 1 into cross multiply this theta 1 to LHS of the above equation. We get theta 1 into theta 1 by theta 3 whole to the power 1 by 4. This is equation, put it in equation 11b. Or approximately it becomes theta by theta 1 equals e to the power lambda by 2, which is nearly equal to 1 plus lambda by 2. 1 plus lambda by 2, where lambda is the logarithmic decrement. Logarithmic decrement, where d is the constant called decrement of the swing. Here theta equals theta 1 into, here cross multiply theta 1 to RHS of the above equation, that is theta 1 into 1 plus lambda by 2, put it as lambda c, 11c, equation 11c. We calculate the logarithmic decrement lambda by observing the first 11 consecutive throws. Here throws 1, 2, 3, 4 up to 11 consecutive throws. Then theta 1 by theta 11 up to 11th consecutive throw, that is equal to theta 1 by theta 2 into theta 2 by theta 3 into theta 3 by theta 4 into theta 4 by theta 5 into so on up to theta 10 by theta 11, that is equal to total 10 throws, e to the power of 10 lambda, e to the power of 10 lambda. That is 10 lambda equals log to the base e into theta 1 by theta 11. Here theta 1 by theta 11 equals e to the power of 10 lambda. Then it becomes 10 lambda equals log to the base e into theta 1 by theta 11. That is lambda equals 1 upon 10 to log to the base e theta 1 by theta 11 equals 2.302 into log to the base 10 into theta 1 by theta 11. The equation 9 corrected for damping is given by charge Q equals T by 2 pi into C by NAB into theta 1 into 1 plus lambda by 2. Dear students, let us see the charge sensitivity of the ballistic galvanometer. The charge sensitivity of the ballistic galvanometer is defined as the charge required to produce a unit deflection or deflection per unit charge, or the charge sensitivity of a moving coil galvanometer is the charge required to produce a deflection of 1 millimeter on a scale kept at a distance of 1 meter from the mirror. By the equation 9, it is written as Q equals Ct upon 2 pi Bna into theta. Let K equals, that is the constant of the galvanometer, that is equal to Ct upon 2 pi Bna. Therefore Q equals K theta. Here charge sensitivity K is equal to, here in this equation, K equals Q upon theta. This is equal to, Q means from the above equation, that is T by 2 pi into C by NBA, that is equal to T upon 2 pi. Here C upon NAB is the current sensitivity. This is current sensitivity of a galvanometer. Here the current sensitivity of a galvanometer is defined as the current required to produce a unit deflection on a scale at a distance of 1 meter from the reflecting mirror of the galvanometer. Some authors defined the current sensitivity as the deflection produced by unit current on a scale kept at a distance 1 meter from the mirror of the galvanometer. Therefore, current sensitivity is equal to theta by I, that is equal to NAB upon C. This is measured in the unit name radian per ampere. The measuring unit of current sensitivity is radian per ampere. With this definition, the figure of merit is the reciprocal of the current sensitivity. The figure of merit is reciprocal of current sensitivity. That figure of merit, the unit of the figure of merit is microampere per millimeter. Thank you one and all.